So now we want to look at solving logarithmic equations. So this is going to be pretty similar to solving exponential equations, except for now the equations will have logarithms in them naturally. But logarithms and exponents are kind of two sides of the same coin, so a lot of the techniques will be similar. So as always, let's start with an example. Let's say we have 2 natural log of x plus 3 equals 7. Okay. So naturally, we're going to want to get the natural log of x part by itself first. So we can just do a little bit of algebra. Just subtract 3 from both sides. Divide both sides by 2. All the normal algebra steps we would do. So we get natural log of x equals 2. So now when we have an equation like this, there's two ways we can think about it. We can either invoke the inverse log property, which says that, okay, if you have something like natural log of x equals 2, in other words, log base e of x equals 2, this is the same thing as e squared equals x, right? These are just, this is just the definition of a logarithm, right? And we called this the inverse log property. So this is fine. So x is equal to e squared. Now, if we, if you don't want to use that property, what you can do is you can do what's called exponentiate. Okay. So natural log of x equals 2 is what we have. So we exponentiate, which means that we take some number and we raise both sides to that number. So in this case, we could do e. So we make this e to the natural log of x equals e squared. So we should, of course, think about if we're allowed to do that. And we are allowed to do that because, again, this is going to follow from the one-to-oneness of the exponential function. Okay, that allows us to do this and keep that equality. So why would we do this? Second, well, we had a log property. I'm struggling to remember what it was called off the top of my head here. It was called the inverse property as well. It was the second version of the inverse property, which said that basically if you have e raised to some logarithm of e, right? In other words, you have some base raised to a logarithm with that same base. These kind of cancel out and we're left with x. And then on the side, right side here, we just have e squared. So that's another way to cancel out the logarithm. So you can just think about it as the definition of a logarithm, or you can exponentiate both sides. Which one's easier might depend on the context. Okay. Now, one thing that's really important when we're looking at logarithmic equations is that logarithms, the domain of the logarithm is not all real numbers, right? Specifically, the domain is 0 to infinity, not including 0. So we have to make sure that when we get our answer, if we plug it back into the original equation, it's going to work, okay? Namely, the original equation, okay, before we do anything to it. When we're given an equation, we're asked to solve it. What we're really saying is, what can we plug in for x that will satisfy this equation? And we can't plug in for, like, just as an example, if we got like -1 as our answer, if we plug that in right here, it doesn't work, right? Because we would have natural log of -1 and that's undefined, okay? So we have to make sure we can plug it back into the original equation, okay? We don't need to check every step because we're gonna, we might change the logarithms a lot, right? We might do a lot of manipulation, but we need to go back to the original. So here we got e squared. E squared is a positive number. It's like, I don't know, like 6 point something, I think. So we can definitely plug that into natural log, no problem. Okay. Okay, let's go to our next equation here. Do 2 natural log of x plus 1 equals 10. Okay. So again, there's not a whole lot to do here. So we'll divide both sides by 2 to get the natural log by itself. And then we can exponentiate, or you can use the definition of a logarithm to get x plus 1 equals e to the 5th. And then you have x equals e to the 5th minus 1. Okay. And this definitely will satisfy the domain of the original problem. Okay. So nice and simple, not a whole lot to do there. All right, let's do log 3x minus 2 minus log of 2 equals log of x plus 4. Okay. Now again, when they don't write the base, it either, usually, hopefully, it just doesn't matter what the base is. Traditionally, again, that means log base 10. Nowadays, it means usually more log base e. But in this case, it's just not going to matter, so we won't worry about it. So let's go ahead and look at how we would solve this. So first of all, everything has a log. Okay, so we could try like exponentiating or something like that, but we would get stuck because of the minus on the left-hand side. What we really want to do is use the logarithm properties in order to condense the left side. So then we just have one log on each side. Okay. So specifically, we use the quotient property to say that this is log of 3x minus 2 over 2 equals log of x plus 4. Okay. And now we just have them both as, we just have the log of something equals the log of something. Okay. So now at this point, again, you could either exponentiate both sides. We don't know what the base is, but it really doesn't matter because the logs would just go away on both sides, right? So if we assume it's e or whatever, we would do e to both sides and they would just cancel out, right? The better way to do it, since we don't know what the base is, better way to think about it is that now we just invoke the one-to-oneness of the logarithm. Okay. The one-to-oneness would tell us, okay, if we have the log of something equals the log of something, those somethings have to be the same number. Okay. So in other words, we can just drop the log. Okay. Equals x plus 4. So this is the one-to-one property of the logarithm. So either way, we'll end up here, and then we can get 3x minus 2 equals 2x plus 8, multiplying 2 on both sides. And bring the 2x over, bring the negative 2 over, we get x equals 10. Okay. Now remember, we need to be able to plug that x equals 10 into the original equation. So if we plug it in here, we're fine. We'll get like 28. We just have to make sure, you can go through and check to make sure you get the actual right answer, but we really just want to make sure it works in the domain more than anything. So here we get, like 28, that's fine. This doesn't have an x in it. This will be 14, so we're all fine on all fronts. So as long as it fits in the domain, we should get the right answer, but you can go through and more thoroughly check it if you would like to. Okay. All right, now let's do a similar one. Natural log of x squared equals natural log of 2x plus 3. Okay. So again, there's not really a lot to do here. It's set up pretty nicely for us. We can just invoke the one-to-one property right away to get x squared equals 2x plus 3. Or you could exponentiate both sides with e, and that'll also cancel out the logarithm. So now this actually is a quadratic, right? So we should bring everything to one side first and then solve it. So we gotta use some of the older stuff to solve these problems still. And then we're gonna get x, what is this, x minus 3, x plus 1 it looks like. So we get x equals 3, x equals negative 1. Okay. So particularly negative 1 should set off some alarm bells because we got to make sure, okay, is this going to work? And if we plug it into x squared, we're good because x squared is always positive, right? We can't plug 0 in there, but anything else, it'll be positive, right? Negative 1 squared is 1, so this is fine. Here, if we plug in negative 1, we're still fine. This is going to be the natural log of 1, which is 0. And that's all fine. Okay. And 3 is also going to be no issue here. So we can plug everything in, no problem. Okay. All right, let's do one. I was trying to find a tricky one here. Let's try this one. 3 log base 2 of 10. 3 divided by log base 2 of 10. Minus log of x minus 9 equals log of 44. Okay, so a couple things to keep in mind with this one. First of all, everything except for that middle log is just a number. Okay, again, they don't give us the base for the log, so you can assume it's 10 or whatever, or e. But like ultimately, we could just get everything to one side except for that middle log, the log of x minus 9. And then we could just kind of exponentiate both sides to get rid of the log. But it would be extremely messy. I mean, it would just be a number, but it would be a really messy number. It would be like one of the ugliest answers we could come up with. So let's do it in a cleaner way. So what I want to do here is, okay, let's make all of these have the same base first of all. We don't know what base these have, but that doesn't really matter. Because what we can do is we can make this have the same base, log base 2 of 10. I think we will need to know what base this is eventually. So I'll check with the book that I'm using if this is log base 10 or e. I'm pretty sure it's log base 10, but we shouldn't need to know until the end. Okay, so using the change of base formula here, we're going to have 3 divided by log base 10 over log base 2, right? Log base 2 of 10 is log base 10 over log base 2. And then we didn't touch the rest of this here. Now this fraction on the left side, we can do our same change flip stuff from the rational chapter. This is 3 log base 2 over log base 10 is what we'll end up with. Right, so you're just basically multiplying by the reciprocal of this. Log of x minus 9 equals log of 44. Okay. So now again, a couple ways we could approach this. Actually, I think that this is where it's important to actually know what the base is. And from the textbook that I'm getting this problem out of, which is the OpenStax textbook, by the way, it does use when they don't write the base, it does use it as base 10. So that's important information here because the easiest way to do this would now be to say, okay, this bottom one, log base 10, that's just 1. Okay. So this is going to be 3 log base 2. So that denominator goes away, which is going to make the problem a lot simpler. Okay, so now, again, a few ways we could approach it. One thing that maybe we could do, first of all, we could use the power rule to bring that 3 into here. So this is log base 2 to the third, which is log base 8. Okay. And now let's get the log with the x, or with the variable with the x over to one side and bring the log 44 to the other side. So we're going to add log of x minus 9 to both sides and subtract log of 44 from both sides. So we're going to have log of 8 minus log of 44 equals log of x minus 9. And now we can combine the left side with the quotient rule. So we're going to have log of 8 over 44. Definitely can simplify that. What would we get? 2 over 11, I believe. So we'll deal with that in a second here. Now these are both the same logarithm with the same base. So we can use the one-to-one property, or you can exponentiate 10 to both sides. Okay. So again, if I write a log with no base, I'm going to make sure to specify what it is. Some of the materials we use, we'll use base E, some will use base 10. If it's on like a quiz or a test or something, I'll make sure to write explicitly what it is. But if I'm getting it from some other source, I'll make sure to write down what base they mean, unless it doesn't matter. Right. Sometimes we want to just use logs without specifying the base because it doesn't matter what the base is. And we want to kind of get used to, being comfortable using those logs without knowing the base if we don't need to know it. Okay. So anyway, these cancel. So we have 8 over 44, which says 2 over 11 equals x minus 9. So we get x equals 9 plus 2 11ths. So 99 over 11 plus 2 over 11 equals 101 over 11. Okay, so a nice exact answer. Like I said, initially, like you could have just brought everything to one side and then just exponentiated and had a really ugly answer, but it would have been the same thing. It would have been 9.2 approximately. But this is just a nicer way to do it. And we got to use a lot of the different log properties on this problem.